Hello everybody, and welcome to the top of page 116 in the workbook. We're going to start looking at the second part of this section, which deals with error approximations for Taylor polynomials. Now, what is this all about? Well, up to this point, we've done a number of examples where we take a function, we build its Taylor series, and we use Taylor polynomials to approximate the value of a function at a point. So these approximations that we were doing, it would be nice to know how accurate they are. How far away are the approximations from the actual value of the function? That's the question that we're trying to answer here. Okay, so let's read this together. So we're starting with a continuous function f with n plus 1 derivatives. Basically, that's just telling us we'd like a function that we can take some derivatives of. And then we're going to let Pn be the nth degree Taylor polynomial for f. Same notation that we've been talking about. Okay, and let's read the next sentence together here. So for a number c, the error that results from approximating f of c by Pn of c is given by En of c equals f of c minus Pn of c. Okay, what are we really saying when we write that? Okay, well, the f of c that you see here, that's just the exact value of our function at some number c. And Pn of c, that's our approximation of f of c that we get by substituting c into the nth polynomial, nth Taylor polynomial. So the error, En of c, is just the difference. It's a measurement of how far apart is the exact value from our approximation. We'd like to come up with a way of estimating how big that error might be. And fortunately, we can do that by looking at the formula below. In particular, it can be shown that the error, the absolute value of the error, En of c, is given by this formula. Let's read it together. M times the absolute value of c minus a to the n plus 1 over n plus 1 factorial. Wow, there is a lot going on in that formula. We've got a lot of symbols there. So let's maybe talk through a couple of those together. Okay, so first of all, the c and the a that you see, those numbers are generally given to you. A is the center point of the series. C is the number where we're interested in doing our approximation, and the value of n we'll generally either know or be able to figure out. Okay, so the one kind of mysterious thing here is this m. What is that all about? Okay, well, m turns out has something to do with the n plus first derivative of our function, and in particular, if we continue this statement down here, m is like an upper bound on the values that we could get out of the n plus first derivative of our function. Okay, and notice that we're saying on a particular interval between a and c. So let's try to explain that again. This is kind of complicated, this part of the formula. The number m, think of that as kind of a worst case scenario. It's the biggest possible value that this absolute value of the n plus first derivative could ever get if we take x values between a and c. Okay, so when we do problems, and we'll do a couple of examples in a minute here, when we do problems where we're trying to approximate the error, one of the calculations that we're going to have to do is to take the n plus first derivative of our function and to figure out what is the biggest that n plus first derivative could get. That's the number m. We'll calculate it and then put everything else back into this formula, and that's going to give us a way of coming up with the biggest possible error that we might get between our function and our Taylor polynomial. Okay, so in the next video, we will actually do an example that shows how all of that works.